Okay, we should be recording.
Okay, good afternoon, everyone. I'd like to welcome everyone to our virtual presentation. My name is, I guess most of you already know me, but I'm a faculty advisor for State LA Baja SAE. And I would like to start by thanking to Dr. Bachman for this wonderful opportunity. So with your guidance, our team achieved phenomenal work. And also, without your guidance, it would have been impossible to achieve this much. And also, my thanks goes to my team, Krystal, excellent team lead. And I can't ask for any more from Krystal. Roy, excellent location tracking team lead, lead. And Edith, the document lead, wonderful, excellent document, such a very technical yet very elegant document that you had produced. I really like your documentation. And image processing lead, Bowen, you did a wonderful job. And hardware component lead, Huang, you also did a wonderful job. And I was so lucky to have you as my team. And you guys did a outstanding work compared to it was just unfortunate that we had to stop, wrap up our project so abruptly due to coronavirus issue. But having said that, now I'd like to share a welcome message from our department.
Okay, so I'm the team lead for the Baja SAE team. Just real quick before I play the welcome messages, we have a Baja SAE team on campus, and as you guys heard, Dr. John Chris Bachman is the liaison for that team. Our project advisors are Dr. Sue, who just gave us our introduction. Sorry, I'm admitting people from the waiting room. And then we also have team members Huang Shu, Edith Vosganians, Roy Chico, and Bowen Waugh. So I'll now be playing the welcome from the Dean, Emily Allen, and Mike Thorburn, who's the head of senior design for the ECST.
Hi everyone, I'm Emily Allen, Dean of the College of Engineering, Computer Science and Technology at Cal State LA. And I'm here to welcome you to our virtual Capstone Expo 2020. That's the Expo that's virtual, not the Capstone projects. In fact, our student teams have been working on their projects since our kickoff in August 2019. That seems like a long time ago now, as the COVID-19 pandemic has forced us into physically distant but socially cohesive modes of operation. We have over 100 project presentations to share live with you over Zoom connections. We are very proud of our excellent senior design program, as it rivals programs nationwide in meeting curricular requirements for design. Engineering design is an iterative, creative, problem-solving process in which science, mathematics, and engineering and computing principles are applied to convert resources into solutions. It has a direct and vital impact on the quality of life for all people. With these stakes in mind, our students have been working hard all year long, and especially these past few months, to finish their projects, and these presentations represent the culminating efforts for their degree programs. We deeply appreciate our project sponsors and industry liaisons, our faculty advisors, and the teams that manage and provide instruction for these capstone courses, including Mike Thorburn and Chris Bachman, John Shamma, Howard Lum, Jason Song, and Rupa Purasengi, Paul Liu, Elaine Kang, Jungsoo Lim, and Raj Pamula, as well as our staff members, Hasmeek Simon and Evelyn Lee. Now, on with the shows, and I'll see you online.
Hi, everybody. I'm Mike Thorburn, and on behalf of the Cal State University, Los Angeles, and the College of Engineering, Computer Science and Technology, I want to welcome you to the 2020 Engineering, Computer Science and Technology Capstone Senior Design Expo. This year, it's a truly unique experience for us and for you, as the Expo will be done live via Zoom. Additionally, sessions will be recorded for those not able to participate in the live event. The students have all worked especially hard to make this event happen and to ensure the audience is able to participate from a safe social distance. Between mechanical engineering, electrical engineering, computer science, civil engineering, and technology, we have about 100 presentations scheduled over a period of about 2 weeks. I encourage you to participate constructively in as many as you can. Your feedback is critically important to the students. As you're watching this video, you must already know about our webpage. If you take time to go through it, you will find detail about all of the presentations and projects. Cal State LA is protecting the event from mischief by using passwords, but if you request access, we'll happily send it to you. The students have been working on their projects since August of 2019. Obviously, the COVID-19 epidemic was a huge disruption over the last month and a half, and it's been hard for everybody. I'm proud to say our Cal State LA engineering, computer science, and technology students, just as they have always done, have shown great persistence to overcome the obstacles confronting them and have made a tremendous effort to wrap up their projects and present them to you now. On behalf of the university and on behalf of these terrific students, I welcome you to Expo 2020.
Okay, so for the rest of our presentation, this is the agenda. First, Huang will go over the background of the project. Then Edith will go over the requirements that we developed. I'll go over how we measured from the CVT. Roy will go over the location collection. Bowen will go over environment collection as well as the user interface. And then I'll wrap the presentation up with the data analysis portion.
Hi, everyone. My name is Huang, and I will introduce you some background information for our project. So Baja SAE is a design competition that teams of students are going to design and build an off-road vehicle, competing with each other, with other 100 universities, both national and also international. The competition includes 2 parts, static and dynamic. And let me introduce you to detail. Next page. So in the static events, there will be professional engineers judge the design of the car. And in the dynamic events, when the car are actually competing. So as you can see, the bordered ones are the ones we impact to. Most of them are in the dynamic events. We are also helping with the design report and the design presentation. We are working with the drivetrain subsection. These are the parts of a drivetrain. What a drivetrain does is to transfer power from engine to the wheel. And the CVT is the transmission we use. By tuning the CVT, it can affect the performance of the vehicle. And let me show you how. So in the picture, this is a CVT. It has 2 parts, which is the primary CVT connect to the engine and the secondary CVT connect to the gearbox. And they are connected by a belt. In the animation, by adjust the weights and spring inside of the CVT, you can change the tune of the CVT. The tune affects the ratio of RPM between the primary CVT and the secondary CVT, and it will eventually affect the performance of the vehicle. For every different situations, for every different situations, like accelerate or hill climb, we need different CVT configurations. So our job is to put sensors on the CVT, do data collection and do data analyze, and help the engineer team to find the best configuration for every different situations. Thank you.
Hello, I'm Edith, and now I will be talking more about the requirements of the project. Listed here shortly. One back, please. Okay, thank you. Listed here are the instrumentation objectives that were established with the help of our liaison and the team. Starting from the top, we're supposed to measure the rotational speed of the CVT primary and secondary, then measure the position of the CVT secondary, which is actually how quickly the secondary opens and closes. Third, measure the vehicle's path, then record the testing course environment, and finally, provide a dashboard for user interaction during testing. Next, I would like to talk a bit about the schedule that we had established for the project. As you can see, we split the operation into 4 parts. The first is the CVT data collection module, followed by location and environment data collection module. Then the graphic user interface was next, which was grouped into the second module, which I will explain shortly. And lastly, our data analysis module. This part unfortunately got cut short in March due to the unforeseen circumstances, but fortunately we were able to gather 1 sample data, which we will talk more about later in the presentation. Now, to expand a little bit more on the modules, here we have how the system architecture was designed. As you can see, we have 2 microprocessors in use, one dedicated to each collection method. The difference between these 2 relies in how fast the data had to be processed. For the CVT data, it was important to not compromise the processing speed with other operations, while the location and environment data could be processed at a slower pace. The RPM sensors and the distance sensors are being collected by the microprocessor 1 as part of the CVT sensor collection without the processing speed compromisation. And the rest falls on the microprocessor 2. This is where we collect the data for the GPS, the location, and the camera, the environment module. In addition, we have the GUI interface, which the user will be interacting with, which will also connect into microprocessor 1 with an SSH to start that collection. We have designed the GUI so that it will have the power to completely start and stop all data collection with 1 click.
So I'm going to be going over the CVT measurement next. And sorry, I'm also having to let in people from the waiting room, so forgive me. Okay, so for the CVT measurement, this meets Instrumentation Objectives 1 and 2, which is measuring the rotational speed of the CVT primary and secondary, as well as the position of the secondary and data collection from the CVT. So for the instrumentation, in order to collect the RPMs from the CVT, we put magnets on the CVT primary and secondary, and you can see that on the left-hand side. In the middle top picture, you can see that as the magnet passes over a Hall effect sensor, it will generate a signal, and that signal is interpreted into an RPM. To make sure that the RPMs that our software is reading were correct, we put reflective tape on the primary and the secondary and used a handheld tachometer to make sure that the readings were matching up. And then in the middle bottom picture, we have the distance sensor placed behind the sheave of the secondary, so as it opens and closes, we can measure its position. In order to keep up with the high speeds of the rotation of the primary and the secondary, we upgraded our system from an Arduino Uno to a Raspberry Pi 4, which has a higher CPU speed, more local memory, and multiple cores in the CPU. And having multiple cores in the CPU allows us to implement multiprocessing in our software. For the architecture of the CVT data collection, first we read values from the sensors. Those values are pushed to a local memory in a multiprocessing queue, which allows multiple processes to access the data so that we can then save the values to solid state drive via USB 3.0 simultaneously. So there's no interruption between the collection and the transfer to non-volatile memory. And the solid state drive and the USB 3.0 port have a higher data transfer rate than a regular USB port.
All right, hello everyone, my name is Chico, and I'll be talking to the location. So my instrument would be tracking the vehicle's path, and our the software would go in the location and environment data collection module. So the instrument I'll be using is called the GPS module, and within that GPS module is the National Marine Electronic Association. which is a organization that standardized the different marine electronics that uses this type of data structure. One data structure that the sentence that they have would be the GPGLL, which pulls the time, latitude, and longitude within that GPS. And I would be using GMplot, which is a Google map plot API to map all the latitude and longitude. All right, first I'll be talking about the GPS limitation. On the top right-hand corner, as you can see in the picture, from my home all the way to the freeway, you can see it was tracking pretty well. However, as I sped up in the entrance to the freeway, my location started going haywire and telling me I was in a different location, as you can see in the second picture. And another limitation I had was when I was testing this during school, I went to different parking structure around our campus and wasn't able to get any data set or any latitude and longitude. I found out that another team, the Baja team actually was also working with a GPS module, and they were also not able to get any data set or latitude and longitude at school. So in order for me to have a good tracking was that around my area, I went around like my block, and it was actually tracking my path pretty well. As you can see, it actually made a complete loop around my area. So what I did was I went, so my speed was less than 40 miles per hour, and I made sure there was no dead zone and no tall buildings around my area. And like I said, you might just have to take the side street because within the side street, there's speed limits, and that's the best way for it to track your path.
Hello, my name is Bowen Waugh, and I will be presenting the environment portion and the user interface portion of our implementation. The main function of the environment implementation is to record the testing course environment. It is related to the location and environment data collection module. These are screenshots taken during previous competitions. While the software is running, we expect these sorts of photos to be taken with the main focus being on the environment and the obstacles. The photos are to be classified by the primary type of object found in them. This is necessary as if there is a drop in the RPM, we can look at the image taken at the time to see if this drop was due to something like an environmental obstacle or some other unanticipated issue. Our plan was to use image AI for the image recognition. As you can see, the algorithm detects and displays objects it recognizes with the probability of the object actually being the object it detects. We got to the point where the program was able to recognize slopes and tires, but not give visual output. Since we were unable to test the program, how the program would perform with photographs from the onboard camera, it is unclear how effective the algorithm would be in testing conditions. I'll now go over the user interface portion. The main function of the user interface is to provide a dashboard for the user interaction during testing. It is part of the graphical user interface, GUI. These two images are the pages which the GUI which the user will interact with. We designed the GUI with the knowledge that most of the people who use it are not tech savvy, and it is for this reason that we chose a simplified design. We didn't want to overwhelm the user with information right off the bat. We used a Kinter library since it is included in most installs of Python and had thorough documentation online. Once the user presses the Start Run button on the left and inputs the text fields on the right and presses the OK button, this data collection will start recording. The moment the OK button is pressed, an Ethernet SSH connection is established between the two Raspberry Pis. The only limitation is that the two Raspberry Pis must be on and is connected to an Ethernet cable. All the processes started and operated simultaneously using the popen command of the subprocesses module. This is the dashboard we were planning to put on the vehicle. it contains all the hardware components of our project. As you can see on the left, the box with the red Raspberry Pi is related to the data collection. The black wires coming off of it would be connected to the Hall effect sensors and the distance sensor. The Raspberry Pi on the right would be located somewhere near the driver, as it has the GUI and it will display all the will display what you just saw on the screen below.
So for the last portion of the presentation, I'll be going over the data analysis that we did. This covers the module number 4 for software deliverables for data analysis. So here we can see the static results that we got from a bench test where the car was up on jacks, and we collected secondary RPM and primary RPMs from the car as we throttled and released the pedal. So you can see that the data is very noisy, and there's what we consider to be shadows underneath the graph. And all this noise needs to be filtered in order for the data to be usable, in order to calculate a ratio between the two RPMs. Here's the results for the distance sensor. So you can see we have these consistent lines, and the values are spread throughout running the bench test. And so what we want to do is find a smooth curve within all this data. In order to do the data analysis, we used MATLAB since it's widely used in the mechanical engineering department, and most of the team members can have a better conversation about the analysis since they have familiarity with it. In order to filter the RPM data, we use remove outliers and paired it with move median. So what this does is that it calculates a local median over a given window size that moves throughout the left to right of the graph, and anything that's more than 3 deviations will be considered an outlier. We repeated this process several times, decreasing the window size for each iteration, and that yielded much cleaner results than leaving the window size large. And then after the outliers are removed, we use move mean to replace instead of remove outliers, and the outliers are considered more than 3 standard deviations from the local mean. And it works the same way, where it has a window size that moves from the left to the right of the graph. We used a different one for the distance sensor since the type of noise was different. We used a Savitsky-Golay filter, and what this does is that it uses the CPU speed and the number of samples per cycle in order to generate a curve in the middle of the graph, which you'll see in a bit. So here's the application of our filter on the primary RPM. In red, you can see the filter data, and blue is the original data. So we can see that we have removed a lot of outliers with a smoother curve, although there were some portions of the graph that had really dense data in the place where the outliers should have been. So those, we have to work on filtering them a little better, but for the most part, it generated usable data. And this is the same filter applied into the secondary RPM, where we can see almost all outliers have been completely removed and the shadows have been removed as well. And so here we can see the data that's clean together for both the primary and the secondary RPM. Here's the results for our Savitsky-Golay filter for the distance sensor, and we have a smooth curve that falls in the middle between all these values and creates a really good distance that we can use to track the position of the secondary. Here we calculated the ratio of the primary and the secondary, and as you can see in black, that's the range of the manufacturer specification, so our ratios fall well within them. Ideally, we want our ratio to even be past infinitely large or infinitely small, but our readings make sense for what we should be seeing for the tune that the vehicle has currently. Here, lastly, we can monitor the shifting behavior of the CVT. So in red, you can see the upshift. And what we would like to have is to adjust that upshift to be much closer than the ideal, which you can see in black, and have the ratio, as the RPM moves higher, have the ratio drop much quicker. And then the downshift depends mostly on the type of dynamic event that we're doing. So the ideal will be different depending on what kind of tests we're doing. But overall, the data that we collected and the information that we got from that data is very helpful in determining what a better tune would be. So if we had more time to use the data acquisition system and do a lot of different test runs, we could compare the upshift behavior and the ratios, as well as some other tests to generate data that we could analyze for this project. Any questions?
Any questions?
So, Krystal, I have a
Yes.
question. So, I might have just missed it, but you also track the position of one of the
The
pulleys,
secondary?
the secondary
Yeah.
pulleys. So how did that match with the gear ratio, as you'd expect those things to be in sync with each other?
Yeah, so they actually have a really similar correlation. They increase and decrease almost exactly the same. If you were to kind of scale the values, they follow each other very, very closely. So here's the ratio, and we can see like the peaks almost match exactly for the secondary. So we're now seeing that that's kind of a really good determining factor of how your ratio is affected by your tune. So that would be like adjusting the spring in the secondary kind of gives you a good idea of how your ratios are behaving throughout your course.
So would you recommend us in the future to only use one over the other? Like maybe, like, is there an opportunity there to maybe only use the distance sensor because it's simpler than the other, or vice? I don't know if it's simpler. Just, is there some opportunity like that for us in the future?
I think even though it's a really good indicator, I would still include the RPM values, just because if you want to calculate, for example, like the shifting behavior, you kind of need both in order to calculate a ratio. And after you calculate the ratio, depending on the type of test you do, for example, like an acceleration run, you want to see the different behavior between the upshift and the downshift as well. And the secondary also allows you to calculate the wheel speed that you're experiencing. And you would miss that information if you only use the distance sensor.
Awesome. That totally makes sense. Thank you guys for all the hard work on this. Nice work.
Thank you.
Yeah.
Does anybody else have questions?
Are we good? Any other questions? Oh, okay, now I would like to say thank you very much to my team. Again, I'm so fortunate to have you guys on my team, and this was one of the best projects that I ever had. And also, I would like to thank you, Dr. Bachman, for your guidance. Would you like to add a few words, Dr. Bachman?
No, yeah, I mean, I think it was really exciting first step. I was super bummed that, I think you guys are ahead of schedule. I think I'd like to continue some of this. And so I think maybe future discussions with team about transitioning some of the equipment and stuff for the team to use this summer would be great, because I think we'd love to use this on the car during different scenarios and stuff. So yeah, I think you guys did an awesome job, and I hope even though you didn't get a chance this semester to put it to use, I hope the Baja team in the future gets to put it to use, and I look forward to thinking of more projects to do with the CS team.
Yes.
So I thought it was great.
Yes.
And thank you, Sue, for all you did with the team. This was a project that we've been trying to do for several years, and we couldn't get much traction, for lack of a better word, but Krystal and the team and Jungsoo has came together really nicely.
Thank you, Dr. Bachman.
Thank you.
I mean, this is a really, really an ideal project that that we can think of. I mean, this has a little bit of hardware and lots of software. Because one of the issues with the computer science field is we don't deal much with the hardware. So that this project will give a very good experience for computer science students that work with the hardware side as well. Good, I'm looking forward to working with this project in the future. Thank you very much.
Thank you, Sue.
Thank you, Sue. It was a pleasure.
Okay, I'm gonna stop recording.